So in vectors, specifically vector differentiation, there is one very important concept called as finding the scalar potential of a vector. Now, what this scalar potential is, we will come to that part. But before that, if I want to find the scalar potential, you have to first of all check whether the given vector is irrotational or not. Now, this concept I have already seen in the previous lecture. How to find whether a vector is irrotational or not. So the next part of this concept or this chapter is finding scalar potential. Now basically, whenever a vector is irrotational, you can always represent the given vector f bar as del phi. Now this phi is called as a scalar potential. Scalar potential. Basically, this phi will come as a function of x, y and z. Function of x, y and z. X, y and z. Or I should better say a scalar function of x, y and z. So I'm going to represent f bar as a scalar function of x, y and z. So the process of finding this scalar function is called as scalar potential. Now how to proceed for finding the scalar potential? Observe carefully. Whatever question you solve, whatever example you solve on finding scalar potential, all the questions will have a standard procedure. So understand the standard procedure. Further, this procedure will also have two different methods of getting the answer. What those two methods are, whichever you find comfortable, you should proceed with that particular method. So what that method are, let us see. Now observe. We already know that this del, it is given as I dou by dou x plus j dou by dou y plus k dou by dou z. Isn't it? So del was given by I dou by dou x plus j dou by dou y plus k dou by dou z. So therefore, obviously, if I give you del phi, it will simply become I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. So that's del phi. Further, I am telling you that f bar is equal to del phi. That's the expression for finding the scalar potential. F bar is equal to del phi. Now let us say f bar, if you observe your question over here that is given, f bar is equal to some function I, some other function j, some other function k. So what I am going to do here is I am going to call this for some time as f1. Then let us call this part as f2 and the last part as f3. So I can write f bar is equal to f1i plus f2j plus f3k. So if I write f bar as f1i plus f2j plus f3k, and I know this is del phi, and previously I have written f bar is equal to del phi. So if f bar, which is the left hand side, is equal to del phi, which is the right hand side, so these two values can be equated. F bar is equal to del phi. So F bar is this value, del phi is this value. So I'm going to equate these two. So if you observe, I can write F1i plus F2j plus F3k is equal to I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. The left hand side is a vector. F1i plus F2j plus F3k. That's a vector. The right hand side is also a vector. I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. So left hand side and right hand side, both of them are vectors. Then for sure you can say that the coefficients of I, the coefficient of j and the coefficient of k can definitely be equated with each other. So that means from here I can say dou phi by dou x can be given as f1, then dou phi by dou y can be given as f2, and dou phi by dou z can be given as f3. So whenever you get any question on finding the scalar potential, this will always remain standard. So what you should be doing? Take the vector f bar, equate it with del phi. So phi is the scalar function of x, y and z. This is what you need to find. This is our target, getting phi. So what I did further, I knew what del was. It was I dou by dou x plus j dou by dou y plus k dou by dou z. Introduce the phi, so it becomes I dou phi by dou x and so on. Then f bar, I already know what the function is given to me. I have written it as f1i plus f2j plus f3k, and I have simply equated the two vectors. Both the components of I, the component of j, the component of k are simply equated. So I've got dou phi by dou x as f1, dou phi by dou y as f2, dou phi by dou z as f3. Now the real process starts. I already have the value of f1, f2 and f3. Let's put up the values of f1, f2 and f3. So dou phi by dou x is equal to, so what's f1 in our case? It is y sin z minus sin x. Y sin z minus of sin x. Then dou phi by dou y, it is this value. I'm going to write that also. Dou phi by dou y is equal to x sin z plus 2yz. And lastly, dou phi by dou z is equal to f3. So I can write dou phi by dou z is equal to, so f3 is xy cos z plus y square. My target is to get this phi. I want to find phi. See how do I get it? If you recall, there was one concept that we have learned in partial derivatives in our previous semesters. So in partial derivatives, if I want to get, say, function phi, so I'm going to write d phi over here. So d phi can be written as dou phi by dou x dx plus dou phi by dou y dy plus dou phi by dou z and dz. That's a very important formula that you have learned in your lower standards. You want to recall it. If you are not recalling it, it's better that you remember it now. It is written over here. D phi is equal to dou phi by dou x dx plus dou phi by dou y dy and dou phi by dou z dz. Now the next thing that you want to do is put up all the values. Whatever dou phi by dou x value is there, dou phi by dou y value is there, and dou phi by dou z value is there. So if I want to get phi, so what I did first is I got d phi. So d phi is equal to this particular expression. Once I get this expression of d phi, whatever the expression comes, the next thing that I'll be doing is simply integrating both end sides. So if I integrate d phi over here, so integration of 1 d phi will give me phi, which will be a function of x, y and z. So how to proceed further? Observe carefully. So dou phi by dou x, what's the value of dou phi by dou x? It is y sin z minus sin x. So I have written y sin z minus sin x, and then ahead I write dx. Then plus dou phi by dou y, it is x sin z plus 2yz. X sin z plus 2yz, and you write dy. And finally plus dou phi by dou z, it is xy cos z, plus y square dz. The next step is quite important, so pay attention how it is done. I'm going to introduce this dx inside the bracket, the dy inside the bracket, the dz inside the bracket. So if I introduce dx inside the bracket, and at the same time, since the solution is too big, so I'm going to arrange the terms also in the meantime. So y sin z into dx, observe carefully. Y is a term of y, sin z is a term of z. So there is y, there is z, and then you get dx. So there is y sin z and dx. I know what the next term is going to come, but I'm going to write a little bit later. This is sin x and dx. So let us wait for some time and write this term a little later. What I've written is there is a term of y, there is a term of z, and then there is dx. Let us find out some other term where you get such kind of an expression. You should be getting y, you should be getting z, and you should be getting x. So if you observe the next term over here, there is x sin z and dy. So I can arrange these terms together. So I'm going to write plus x sin z and dy. If you observe carefully, you can find one more term where x, y and z are going to come together. Observe the last term. There is x, there is y, and then there is cos z. So what I have done here is I have gathered terms which contain x, y and z together. So there is xy cos z and dz. So I'm going to write that also over here, xy cos z and dz. So basically the concept says whenever this dx, dy and dz terms are present, what you should be doing is start collecting terms which are individually depending on the same variable, like sin x. Sin x does not contain y, does not contain z, so it will be always accompanied with dx. So I'm going to isolate that term and write it a little later. Then if you observe here, there is y and z, and then there is dy. There is no x present. That means the next time I'm going to find those terms which contain only y and z. So my first term was y sin z and dx. So there is y, there is z, there is x. The next term x sin z and dy. Again there is x, there is z, and then there is y also, dy. Then xy cos z. Obviously it contains all the variables. X is there, y is there, and z is there. So collection of the terms is very important over here. So wherever you find three variables together, get them together. Wherever you find two variables together, get them together. Wherever you find a single variable, you isolate those terms. So isolated terms will be definitely sin x and dx. That is the only term which does not contain y and z. Now, as I said, dx was multiplied with the first term, dy was multiplied with the first term here, and dz was also multiplied with the first term over here. Still few of the terms are left. Minus sin x dx. As I said, it is an isolated term, so I'm going to leave it aside for some time. The next term is 2yz and dz. So I'm going to write plus 2yz and dz. That's a term of y and z. So my objective is to find some other term which will contain y and z. So if I go ahead, so this was my multiplication here, 2yz and dy. If I go ahead, look at this term which contains y square and dz. That means it contains y as well as z. So all terms which contain y and z should be brought together. I'm going to write plus y square and dz. One final term is left, which is minus sin x dx. Let us write that also, minus of sin x and dx. So you need to pay attention how the terms were arranged. I have multiplied dx, dy, dz inside the bracket, but at the same time I have arranged the terms, and how the arrangement was done, it is based on the variables. That means in the first term I have y, I have z, and x is getting multiplied inside. So there is x, there is y, there is z. I will find every single term which will contain these three variables, x, y and z. Then the next was y and z. So I will find all those terms which contains the variables y and z. So that's my arrangement. Now the real challenge comes. I am going to take all these three terms collectively and I am going to write them in some new pattern. Observe carefully how the pattern is written. You can see y, you can see sin z, and you can see dx over here. So dx is basically the derivative of x. So I had x and its derivative is dx. Next term is x and sin z, and then there is dy. So if you observe, there was y and then its derivative is dy. See, as I said x, its derivative is dx. As I said y, its derivative is dy. Similarly, if you go to the next term, there is cos z and then there is dz. So if I write the terms like this, x, y, pay proper attention what is written, x, y and sin z. So this is actually u into v into w. So when I say u into v into w, derivative of u into v into w, how do I find the derivatives? So derivative of u, v and w kept as it is. That means y and sin z will be kept as it is, and derivative of x becomes dx. That's the term here. Y and sin z as it is, derivative of x becomes dx. Next term, derivative of v, keeping x and sin z as it is. So as I said, derivative of y, it is going to be dy. So see, x and sin z kept as it is, and then you get dy. And the last derivative, see, keeping u and v as it is, x and y as it is. So x, y kept constant. Derivative of sin z is going to be cos z, and since it's a term of z, I will write dz ahead of it. So that's how you get xy cos z dz. Now this is done only and only by sheer observation. You have to observe the terms very carefully to decide what is going to come. Similarly, observe carefully. These two terms again I am going to take together. So if I take these two terms together, observe here, what do I see? I see y square. So if I ask you the derivative of y square, it is 2y. See, it is 2y present over here. If I ask you the derivative of z, it is dz, which is present over here. So I can now write, so that's 2y, sorry, this is y. This is y. Okay. So if I ask you the derivative of y square, it was 2y, it is present over here. If I ask you the derivative of z, that is dz, which is present over here. So the term over here that I should be writing is plus d of y square, the derivative was 2y, and the derivative of z was dz. So I write d of y square z. So see, that's simply u into v rule. If you take u into v rule, first term as it is, y square as it is, derivative of z will become dz. So y square and dz, that's the term present over here. Similarly, z as it is, derivative of y square, it is going to be 2y. You are differentiating y, that's why dy will also come. So 2y, dy and z will also come. So that's your derivative over here. This means the entire big bracket has been now transferred into a very small bracket. D of xy sin z, d of y square z. Now, nothing happens to minus of sin x dx. Whichever are isolated terms, you leave them as it is. That means I'll simply write minus of sin x and dx. Now people remember, this entire thing that you have got is the value of d phi. It is a value of d phi. Now, if I ask you to integrate 1 with respect to dx, integration of 1 dx, you write x. So similarly, if I ask you integration of 1 d of some variable over here, whatever the variable comes, even if I write log z, d of log z. So integration of 1 with respect to d log z, the answer would be log z. Integration of 1 with respect to d sin x, the answer would be only sin x. You got to understand this, how it is written. So whenever the integration is taken on both the sides, obviously if there is a derivative, you simply get the function as it is. That means if I integrate both sides here, if I integrate both sides, so I get integration of 1 d phi, integration of say 1, you can write d of xy sin z, then plus integration of 1 d of y square z, and then minus integration of sin x dx. So obviously integration of 1 with respect to d phi, that gives me phi, is equal to integration of 1 with respect to this big variable. So the answer is going to come xy sin z. Integration of 1 with respect to this variable y square z. You are going to get y square z. And obviously it's a single variable integration. Integration of sin x, you all remember, it is minus of cos x. So minus and minus becomes plus. So that gives me plus cos x. And all over we have taken integration, not to forget to put plus c. So that is what your scalar function phi comes out to be. So that's how we get f bar is equal to del phi. So phi is called as a scalar potential. So this is what a scalar potential has come. If you observe, it does not contain any vector form. There is no r, there is no j, there is no k. Only pure scalar has come, and that is a function of x, y, and z. So this function is called as a scalar potential of the vector f bar. Look at the process one more time, how it was done. So f bar was taken as del phi. Then what I did, I know del, I know what I have to find phi, so I've got del phi. So equating f bar with del phi, I've got some relations. F1, F2, F3 were already known to me. I've equated what the values of dou phi by dou x, dou phi by dou y, dou phi by dou z with F1, F2 and F3. And then I should not forget to remember this particular formula d phi, which was we have learned in semester 2. Total derivative. So d phi is equal to dou phi by dou x dx and so on. Put up all the values. Start collecting those terms which contain the same variables. I have y, z and x is coming from outside. So x, y and z. All the three variables should be together. So in the entire expression, I should start finding those variables which contain x, y and z. So I've paired all the terms of x, y and z together. Then you have to integrate both the sides. So remember, integration of 1 dx, it is x. So likewise, integration of 1 d, some big variable, the answer will be simply that variable. This is one of the way of getting the answer. Sometimes this method becomes slightly tricky. There is another way of getting the same answer, but then it is slightly lengthy. Observe what I am doing. I have dou phi by dou x, dou phi by dou y, dou phi by dou z. What I will be doing is I am going to integrate this term straight away here only. That means the integration of dou phi by dou x with respect to x, integration of dou phi by dou y with respect to y, and integration of dou phi by dou z with respect to z. Let's see what the answer comes. So integration of dou phi by dou x. So that's the other method of getting the same answer. Method 2. Whichever method you feel comfortable, you can continue with that method. So integration of dou phi by dou x dx. So that's going to come. Integration of y sin z. Integration of y sin z minus of sin x and dx. So we know integration is carried out with respect to x. That means the term of y and z should be kept as constant. So y and z both are constants. Go outside the integration. One is left. Integration of one is x. I get x y sin z minus of integration of sin x is carried out with respect to x. So this will become minus cos x. So that becomes plus cos x. Since integration is carried out under the variable x, but I have other variables y and z also. So I should not forget to write plus phi 1 of yz. It's a function of y and z, which is not known to me. So I have written phi 1 of y and z. Similarly, integration of dou phi by dou y with respect to dy, that would come integration of. So now what's dou phi by dou y? X sin z plus 2yz. So it is x sin z plus 2yz. Integration is carried out with respect to y. You write dy over here. So now, if you take the first term, it is x and sin z. That means it is completely a constant. X and sin z, both of them are constants. So they both go outside the integral. One is left. Integration of one is y. So I get x, y, sin z. Then plus, in the second term, I have to integrate 2yz, of which 2 and z are both constant, so they go both outside the integral. 2 and z went outside the integral. Y is left, its integration is y square upon 2. And outside 2yz, 2z was there. So 2 and 2 cancels, you get y square z. Plus, integration is carried out with respect to y. And there are still two more variables left, which I don't know. Hence, I write plus some function of, since it's integration with respect to y, you write x and z over here. And finally, let's take the last function, dou phi by dou z and dz. That's integration of. So what's dou phi by dou z? So I have dou phi by dou z as xy cos z plus y square. So I have x y cos z plus y square. Integration is carried out with respect to z. So if I am going to carry out the integration with respect to z, x is constant, y is constant, they both go outside. Integration of cos z with respect to z is sin z. So I'll write x, y, sin z. Then plus integration of y square. Now since integration is carried with respect to z, y square becomes a constant for that term. Y square goes out and you write y square z. And since the variable is z, I don't know what the function of x and y is, so I write function of x and y. Observe the three relations that you have. The first one, that's the second one, and that's your third function. These three functions are going to give us the value of phi. Now how it will give us? Observe the three functions. Whichever terms are repeated once or twice should be written only once. If you observe the first term x, y, sin z, repeating in all the three relations. So that will be written only once. So x, y, sin z, only once I will write. Then I can see cos x. Nowhere cos x is present, so that cos x will also come. See, cos x is already there. And then if you observe, there is y square z, and then there is y square z, which is repeating 2 times. So xy sin z was repeating 3 times, but still it will be written only once. Y square z is repeating 2 times, but still it will be written once. And one final term, that was cos x, will also be written in the function. And as we are carrying out integration, c should be written. Now, if you remember, derivative and integration, if they come together, you get the function phi. So it is like d phi by dx integrated with respect to x. you should get phi. Dou phi by dou I integrated with respect to y, you again get the function phi. You again get the function phi. So it does not mean you are getting function phi 3 number of times. It simply means phi is obtained from any of these 3 steps, but the problem is when I'm integrating with respect to x, I don't know what y and z is going to come. When I'm integrating with respect to y, I don't know what is x and y going to come. When I'm x and z I'm going to get. Similarly, when I'm going to integrate with respect to z, I don't know what x and y functions are going to come. So these 3 should be combined together to get the final answer. So these are the 2 different ways in which you can find the scalar potential function. I hope you have understood. Note it down.